Attention is insanely powerful. It works because every token can directly talk to every other token. That's why transformers dominate language models. But attention has a brutal downside. The cost grows quadratically with sequence length. Compute explodes, memory explodes, and during training, you literally have to materialize the full attention matrix on GPU unless you use tricks like flash attention. Even then, the scaling problem doesn't disappear. Now, here's the important realization. The real problem is not just quadratic complexity. The real reason attention works so well is that it does content-based routing. Tokens don't just interact because of position. They interact because of meaning. Most efficient alternatives like linear attention, convolutions, or classic state space models lose this ability. They compress history, but they do it blindly. So the question becomes deeper than how do we make attention faster? It becomes how do we compress long context without losing the ability to reason over content? This is where Mamba comes in. Before transformers, sequence modeling was dominated by recurrent networks, RNNs, LSTMs, and grooves. They process sequences step by step, maintaining a hidden space that summarizes the past. Mamba builds on this idea, but in a much more principled way. At its core, Mamba is a simple state space model. There's an internal state that evolves over time using learned dynamics given by HT here. Traditionally, these models are time invariant, meaning the same rule applies at every step. That makes them efficient, but also their biggest weakness. They can't decide what to remember and what to forget based on the content itself. Mamba fixes this with one key idea, selection. Instead of keeping the state dynamics fixed, Mamba makes them input dependent. The model learns at every time step whether the current token should be ignored, partially remembered, or completely override the state. In other words, the compression becomes content aware. This turns the state into something intelligent, not just memory but selective memory. Now there's a catch. Once the dynamics depend on the input, you can't just use fast convolutions anymore. The model becomes fully recurrent, which normally would be slow and memory hungry. The authors solve this with a hardware-aware trick. They design a fused parallel scan algorithm that runs efficiently on GPUs, keeps most computation in fast SRAM, avoids storing huge intermediate steps, and even recomputes values during backprop to save memory. The result is linear time, linear memory, and very high throughput. There's one more important detail. These models are defined in continuous time, but neural networks operate in discrete steps. Mamba uses a careful discretization that turns the continuous dynamics into something very similar to a learned gate like in Groove. That's why the Mamba can reset its memory, persist information indefinitely, or ignore noise entirely.